Hi students, in the last video we discussed about different sample spaces and the events and what are axioms of probability. So now we'll discuss about joint probability and conditional probability in this video. So in order to define this joint event or joint probability, I am taking two events, event A and event B. Two events I am taking, event A and event B. And the joint event can be taken as A intersection B, or you may also take A union of B. Two events I am taking. So now, what is the occurrence of this joint event A intersection B or A union B? It can be defined as probability of A intersection B is equal to probability of A plus probability of B minus probability of A union B. And the occurrence of A union B is taken as probability of A plus probability of B minus probability of A intersection B. So these are the two equations which can give you the joint probability of two events or any number of events or simply multiple events. Suppose if event A and event B are mutually exclusive, if A and B are mutually exclusive, then you know already the probability of A intersection B is equal to 0. So there is no common element if A and B are mutually exclusive. So therefore, probability of A union B is equal to probability of A plus probability of B. You need to remember this one. This is very important. If A and B are mutually exclusive, then union of the two can be taken as the sum of the two events probability. Simply. Okay. Next, take the conditional probability. So conditional probability can be taken with respect to one already existed event. Suppose I have two events A and B, again, two events A and B. Now I'm going to define the existence or the occurrence of the probability of A with respect to probability of B. And here the probability of B or the B event is already existed. Event B is already occurred. So with respect to occurred event, you need to define probability of the new event. So simply I can take probability of A by B. So probability of A for the given event B. This is the way you need to define probability of A with respect to the existed event B. So that is defined as probability of A intersection B divided by probability of B. Okay, so you can take one example, simple example. So take your examinations. So if you have event B is the student must have attendance greater than 75%. And A is then only you are allowed to write the exam. So these are the simple examples for conditional probability. And if A and B are mutually exclusive, if A and B are mutually exclusive, then probability of A intersection B is equal to 0. So if probability of A intersection B is equal to 0, probability of A by B is also equal to 0. Okay. And since the probability of one event is defined with respect to already existing event, so this conditional probability is taken as a defined quantity. So when the probability is a defined quantity, it must obey the three axioms. Obey three axioms what we have. So we need to prove whether this conditional probability is satisfying the three axioms or not. So let us take the first condition, axiom 1. Axiom 1. So what is the axiom 1? Probability of the event always greater than 0. So here the condition axiom 1 is, sorry, 0, or it must be 0 to 1. Okay. And here probability of A by B is given as probability of A intersection B divided by probability of B. And here the probability of B is already occurred, so there is no negative value, and probability of A intersection B is also a non-negative value. Then automatically probability of B is always greater than or equal to 0. Okay. And the axiom 2. What is axiom 2? Probability of S is equal to 1. Okay. So now I am taking simple assumption here. Take sample space S is equal to A. So therefore probability of S by B is equal to probability of S intersection B divided by probability of B. So already you know all the events are subset of sample space. So probability of S intersection B is probability of B only. So probability of B, the 2 gets cancelled and the answer is 1. So probability of A by B is equal to 1. So axiom 2 is also satisfied. And coming to axiom 3. So what is axiom 3? Probability of union I is equal to 1 to n AI is equal to sigma I is equal to 1 to n probability of AI. So this is going to be small n, you can take. Okay, so in order to prove this one, I'm taking one event here in an extra event. So consider event C. So I'm taking one extra event C, and assume that event A, event B, event C are mutually exclusive. Mutually exclusive. So if A, B, and C are mutually exclusive, then A intersection B, A intersection C, and B intersection C are also mutually exclusive. Okay. So now my task is to prove this condition. So for this purpose, I'm taking that probability of A union C by B. Probability of already B is given. So what are the other elements? A and C only. So that's why I'm taking probability of A union C by B for the given event B. So what you need to prove? Probability of A by B plus probability of C by B. So this is the statement we need to prove in order to satisfy axiom 3. Okay. So now for this purpose, I'm taking simple modification as per the conditional probability definition. So what is that? Probability of A union C by B is equal to, this is simply A by B formula. Then I am taking probability of A union C intersection of B divided by probability of B. So all are mutually exclusive. All are mutually exclusive, and I am taking simple modification here, that is A union C intersection B is written as A intersection B union A intersection C. Sorry. I can write this as A intersection B union of C intersection B divided by probability of B. So now all are mutually exclusive. So you can write this as probability of A intersection B plus probability of C intersection B divided by probability of B. And it can be taken as A intersection B divided by probability of B plus probability of C intersection B divided by probability of B. So I can write this as A by B simply A by B plus this can be written as C by B. So therefore, finally, probability of A union C for the given event B is proved. Hence, this condition also satisfying axiom 3. Finally, since the conditional probability definition followed axiom 1, axiom 2, and axiom 3, it is a default probability function. Okay. Thank you for watching.